If you've ever been confused by the difference between a server and a desktop computer, you're not alone. By the end of this video, you'll understand exactly what a server does, how it works, and when you need one instead of a regular PC. In everyday computing, people often use the words desktop and server as if they mean the same thing. In reality, a server is a specialized system designed to provide services, data, or resources to other computers over a network. A desktop, by contrast, is a general-purpose personal computer intended primarily for one person at a time. Both are built from familiar components such as processors, memory, storage, and networking, but they are designed with different priorities. Stay with me until the end as we take a deeper dive into what servers do, how they work, and the key differences that set them apart from desktop computers. A server is a computer system or software service that responds to requests from other devices, commonly called clients. The idea is central to networking. One system hosts a resource or service, and other systems access it when needed. For example, when a user opens a website, a web browser sends a request to a web server. When an employee opens a shared folder, the request is handled by a file server. When an application stores or retrieves information, it often interacts with a database server. In each case, the server's job is to remain available, process requests efficiently, and return the correct result. The term server can refer to both a role and a machine. In a small environment, a desktop-class computer might act as a server by sharing files or hosting a lightweight application. In enterprise environments, however, the word usually refers to dedicated hardware and an operating system configured specifically for server workloads. Modern server platforms are optimized for continuous operation, centralized administration, multi-user access, security hardening, and growth over time. According to Microsoft's Windows Server documentation, server platforms are designed to build and manage infrastructure for connected applications, networks, identity services, storage, virtualization, and web services rather than only supporting a single local user session. A server can perform multiple roles simultaneously. In addition, these roles can be distributed across multiple servers as needed to meet performance, scalability, or redundancy requirements. The following are some of the common roles a server can fulfill. A web server is a service that delivers web pages and application content over the internet using the Hypertext Transfer Protocol. An application server is a service that runs business applications or middleware. A database server is a service that hosts structured data and processes queries. A file server is a server that stores and shares files for users and applications. A mail server is a server that I am sure most of you have come across. It is a server that sends, receives, and stores email. A DNS or DHCP server is a critical network service that forms the foundation of modern networks and the internet. It supports essential functions such as network name resolution through DNS and automatic IP address assignment through DHCP, enabling devices to communicate efficiently across a network. A directory server is a centralized database-like system that organizes, stores, and manages information about users, devices, and resources on a network. It acts as a digital address book, allowing IT administrators to securely control who has access to what, enabling single sign-on and authenticating credentials. A virtualization host is a server that runs multiple virtual machines on a single physical computer using a hypervisor. A backup server is a server that centralizes backups and recovery operations. And a print server is a server that manages printers and print queues for many users. Servers are optimized for uptime, throughput, and concurrency, not for interactive desktop use. For this reason, servers typically have multiple CPUs with a large number of cores. The emphasis is on running many threads simultaneously rather than maximizing the speed of individual threads. Although this does not mean servers are slow. Servers also tend to have large amounts of RAM and storage capacity and are equipped with high throughput network interface cards to handle the large workloads they deal with on consistent basis. Servers are expected to operate 24/7 and prioritize stability and reliability. For this reason, they often include redundant power supply units and use error-correcting code in their memory, which can detect and correct certain types of memory errors to improve system reliability. On the software side, servers run daemons, which are silent. They are tireless background programs that run continuously listening to ports without needing direct interaction from a user. They wait for specific requests or events, perform their assigned tasks, and keep the server operating smoothly. Examples of server daemons are web services, secure shell, and DNS services. These services are defined by the protocols through which they are accessed, rather than by the hardware which they run on. As mentioned previously, servers are designed to handle requests from multiple clients in parallel, and frequently operate in a headless configuration, meaning they do not require a graphical user interface. Administration is typically performed remotely using technologies such as SSH, RDP, or baseboard management controller interfaces. A desktop computer is a personal computer designed primarily for interactive use by one person at a time. It is usually optimized for tasks such as web browsing, office productivity, media playback, design work, software development, or gaming. Desktops emphasize user experience, affordability, local peripherals, and responsiveness for foreground applications. They commonly include a full graphical interface, local keyboard and mouse input, audio support, and direct monitor output, because they are meant to be used as someone's everyday workstation. Desktop systems are typically turned on when a user needs them and powered down or put to sleep when not in use. Their design priorities often include purchase cost, ease of use, quiet operation, good graphics performance for local applications, and compatibility with a wide range of consumer hardware. Although some desktops can be very powerful, their power is usually directed towards serving the person sitting in front of them rather than servicing many simultaneous requests over the network. To understand the difference between servers and desktops, it helps to understand the client-server model. In this model, the server provides a service, while the client requests and consumes it. A client can be a desktop, laptop, tablet, phone, point-of-sale terminal, or another server. For example, a desktop user can log in to a company domain, open files from a network share, browse a website hosted on an internal server, and authenticate to an application that stores data in a database server, all in the same work session. This architecture separates responsibilities. A desktop focuses on user interaction. A server focuses on delivering a dependable service. That separation is valuable because it allows organizations to centralize data, apply consistent security rules, back up important systems, patch infrastructure in a controlled way, and scale resources according to demand. In many environments, a single employee may rely on dozens of servers without being aware of it. Identity servers verify sign-in credentials, storage servers provide documents, mail servers route messages, and web or application servers power internal business tools. The simplest way to state the difference between a desktop and a server is this. A desktop is built mainly to help one person do work directly, while a server is built mainly to provide services reliably to many users, systems, or applications over a network. From that single distinction flow nearly all of the other differences in hardware choices, operating systems, expansion features, cooling, redundancy, management tools, and security controls. Servers and desktops both contain CPUs, memory modules, storage devices, network adapters, and motherboards, but the components are selected for different goals. Desktops generally prioritize cost, burst performance, graphic support, and low noise for local use. Server hardware prioritizes reliability, serviceability, expansion, and sustained performance under constant load. Enterprise server systems often support features not found in standard consumer desktops, including multiple processors or higher core count processors, larger memory footprints, ECC memory, remote management controllers, hot swappable drives, redundant power supplies, and rack mount form factors. Desktop processors are usually tuned for fast response in interactive tasks, where a single user launches programs, opens files, or runs applications that benefit from strong single-threaded speed. Server processors, by contrast, are commonly optimized for heavy parallel workloads, large memory support, many simultaneous threads, and long-running operation. A desktop might be expected to open a spreadsheet quickly or render a design smoothly on one screen, while a server may need to handle hundreds or thousands of web requests, authenticate many users, run several virtual machines, or process many database transactions at once. Before we move on to the next slide and talk about server RAM, I have a quick pop quiz for you. Do you know what the theoretical maximum RAM capacity of a 64-bit computer is? Think about your answer for a moment, and I will reveal it after our next segment. One of the clearest hardware differences between servers and desktops is the server-side support for ECC memory that can detect and correct certain kinds of bit errors in RAM. On a personal desktop, a rare memory error might cause an application crash or an occasional system fault. On a server that stores critical business data or runs continuously for months, even rare memory corruption can be far more serious. Because of this, server platforms often treat ECC memory as a standard reliability feature rather than a luxury. Servers also tend to support far more RAM than desktops because many server workloads, especially virtualization, databases, caching, and analytics, are memory intensive. Remember that pop quiz from a couple of slides back about the maximum amount of memory a 64-bit computer can have? The answer is a mind-boggling 16 exabytes, or 18.4 million terabytes of RAM. That's the theoretical memory limit of a 64-bit system. To put that staggering number into perspective, here's an interesting extrapolation. If you filled that amount of memory entirely with text and printed it out, the stack of paper would stretch over 800 million kilometers, or approximately 497 million miles. That is more than 5 times the distance from Earth to the Sun. Populating a computer today with 16 exabytes of RAM is theoretical and practically impossible. Theoretical because that amount of memory exceeds the RAM production capacity of the world for an entire year. Not only that, housing such large amount of hardware will require a massive dedicated data center facility with millions of free square footage that is equivalent to roughly 5 Empire State Buildings. I would say you would really need a huge backyard for that fully populated computer of yours if you ever intended to build such a behemoth. Is your mind boggled yet? If not, here are a couple more facts for you. Using top-end enterprise DDR5 RAM modules at 128 gigabytes apiece would require approximately 131 million memory sticks to populate that 16 exabytes of RAM to full capacity. If this memory contraption was to ever be built, it would consume around 12 gigawatts of power, more than the total electrical output of 10 average nuclear reactors, and would require thousands of servers just to rack that amount of RAM modules inside them. Desktops often have 1 or 2 storage devices selected for capacity, cost, or application speed. Servers are more likely to have multiple drive bays, dedicated storage controllers, and configurations designed for resilience as well as performance. Hot swappable drive bays allow failed disks to be replaced without shutting down the system. Servers also commonly use RAID configurations to improve availability and, in some cases, performance. In business environments, this matters because disk failure should ideally degrade service gracefully rather than bring the entire system offline. Most desktops have a single power supply and are cooled for intermittent bursts of activity and ordinary room conditions. Servers, especially those in racks or data centers, are built for continuous sustained workloads and denser thermal environments. Many include redundant power supplies so the system can continue operating if one power module fails. Their cooling systems are usually louder and more aggressive because their objective is dependable operation rather than a quiet desk-side experience. This difference reflects a broader theme. A desktop is expected to be convenient for a user, whereas a server is expected to stay running. Although desktops and servers may run operating systems from the same family, such as Windows, they are not necessarily the same operating system. While they share compatibility and many applications can run on both versions, each edition is designed and optimized for different purposes. The operating system on a server is usually chosen for stability, remote administration, security controls, automation, and support for infrastructure roles. Common examples for server operating systems include Windows Server and server-focused Linux distributions. Desktop computers, on the other hand, run operating systems such as Windows 11, Mac OS, or consumer Linux distributions, and they are optimized more heavily for local interaction, multimedia, device compatibility, and personal productivity. Server operating systems are built to install and manage roles such as directory services, DNS, DHCP, file sharing, web hosting, virtualization, update services, and failover clustering. They can often run with little or no graphical interface, especially in hardened or resource-conscious deployments. This is very different from a desktop where the graphical experience is the main method of interaction. In many cases, administrators manage servers remotely through web consoles, PowerShell, secure shell sessions, or centralized tools rather than by sitting in front of the machine itself. A desktop operating system is designed so that a user can log in locally, open applications, connect accessories, use audio and graphics features, and customize the interface easily. In contrast, a server operating system is designed to provide predictable background services. It generally favors administrative controls, policy enforcement, remote access restrictions, auditing, and role-based configuration. This does not mean a server cannot display a desktop interface, only that the interface is secondary to the infrastructure function. Desktops and servers are both capable computers, but they are tuned for different workload shapes. Desktop workloads are often interactive, bursty, and user-driven. They are primarily used for opening applications, editing documents, compiling code, browsing the web, or manipulating media. On the other hand, server workloads are often persistent, multi-user, and background-oriented. They are designed and optimized to handle and respond to network requests efficiently, replicate data, run scheduled jobs, host virtual machines, index content, or store shared resources. Because servers operate under constant or near constant demand, performance is measured not only by peak speed, but also by consistency under load, throughput, latency at scale, and recovery behavior when components fail. A desktop is usually judged by how quickly it feels to a single user, while a server is judged by how well it serves many requests at once. This can include concurrent users accessing shared folders, customers visiting a website, applications querying a database, or virtualizing multiple hosts among many other services. That is why servers often invest in more cores, more memory channels, faster network interfaces, and storage architectures that reduce bottlenecks across many simultaneous operations. Perhaps the most important practical difference between a server and a desktop is the expectation of uptime. A desktop can be rebooted at lunch, shut down at the end of the day, or taken offline for maintenance with limited impact. A server often supports many users or an essential business function, so downtime can disrupt operations across an entire team or organization. Because of this, servers are designed with availability in mind. ECC memory, redundant power, multiple network interfaces, RAID or other resilient storage configurations, firmware management tools, and in some cases, clustering or failover designs. High availability does not mean a server never fails. It means the system is engineered to reduce the chance of failure, detect issues early, and recover in a controlled way. For example, if a server has mirrored disks and one fails, the service may continue while the bad drive is replaced. If a server has two power supplies and one stops working, the remaining unit can keep the system online. If workloads run in a virtualized cluster, another host may be able to restart an affected virtual machine. Desktops, in contrast, generally accept more risk because the impact of failure is smaller and localized. Storage design is one of the clearest examples of how servers emphasize resilience. A desktop may have one SSD for the operating system and applications, plus perhaps another drive for personal files. A server may hold the data for an entire team, an online service, or a business database, so it often uses RAID. RAID, or redundant array of independent disks, combines multiple physical drives into a logical storage set to improve fault tolerance, performance, or both. Common levels include mirrored arrangements for high redundancy and parity-based arrangements for balancing protection with usable capacity. It is important to note that RAID is not the same as backup. RAID helps keep a system running when a drive fails, but it does not protect against accidental deletion, ransomware, corruption that is replicated across multiple drives, or site-wide disaster. Servers, therefore, tend to participate in broader data protection strategies that include snapshots, external backups, replication, retention policies, and recovery testing. Desktops can be backed up too, but centralized server data usually receives stricter governance because many users depend on it. As mentioned previously, RAID is a method of configuring multiple hard drives to work together for improved performance, redundancy, or both. However, RAID does not define how or where the drives are physically installed or connected. Those aspects are addressed by storage architectures such as DAS, Direct Attached Storage, NAS, Network Attached Storage, and SAN, Storage Area Network. DAS, Direct Attached Storage, refers to a storage system in which multiple hard drives or SSDs are installed within a single enclosure and connected directly to a host computer or server, rather than being accessed over a network. NAS, Network Attached Storage, is a dedicated storage device that contains one or more hard drives or SSDs and is connected to a network, allowing multiple users and devices to access and share files over that network. And SAN, short for Storage Area Network, which is a high-speed dedicated network that provides shared storage resources to multiple servers. Unlike NAS, which shares files, a storage area network configuration presents storage to servers as if the hard drives were locally attached devices. Let's take a closer look at how desktops and servers function at the network level, the differences, and what is expected from each. A desktop uses the network mainly to reach or consume services, such as websites, cloud applications, printers, file shares, email systems, and collaboration tools. In contrast, servers use the network primarily to provide those services among many others. As a result, servers often have more network interfaces, faster adapters, support for segmentation or bonding, and configuration tuned for incoming connections, traffic control, and service isolation. In an office, users may barely think about networking until the Wi-Fi slows down. In a server environment, network design is part of the platform itself because communication is the foundation of the server's job. Modern servers are rarely limited to one operating system or one application per physical machine. A major characteristic of server environments is virtualization, in which one physical server hosts many virtual machines or containers. This allows organizations to consolidate workloads, improve hardware utilization, isolate services, simplify backup strategies, and move workloads between hosts more easily. Server operating systems and hypervisors are built with this in mind. Desktop computers can also run virtual machines, but usually as a secondary function for development, testing, or training, rather than as the core purpose of the hardware. Virtual machines, VMs, and containers are both technologies used to run applications in isolated environments, but they differ in how they achieve isolation and utilize system resources. A virtual machine emulates an entire computer system, including its own full operating system, making it highly isolated and capable of running different operating systems on the same physical hardware. This strong isolation comes at the cost of greater resource consumption, larger storage requirements, and slower startup times. Containers, on the other hand, share the host operating system's kernel and package only the application and its dependencies. As a result, containers are much lighter, start almost instantly, and allow many more workloads to run on the same hardware. VMs are typically preferred when strong security boundaries, legacy application support, or multiple operating systems that are isolated at the hardware level are required. While containers are ideal for modern cloud-native applications such as Netflix and Uber, they are also well suited for deploying microservice-based architectures. That is where large applications are broken down into a collection of smaller independent services and then redeployed as containers. Also, the lightweight nature and portability of containers makes them particularly effective in environments that require rapid deployment, frequent updates, and scalable application delivery. Unlike virtual machines, VMs, containers do not include a full operating system. They share the host machine's OS kernel, requiring far less CPU, memory, and disk space. However, this also means that if the host OS kernel fails, the containers running on it will crash as well. While a platform like the standard Docker engine is excellent for creating and running individual containers on a single computer, a business environment requires managing hundreds or thousands of connected containers. At scale, managing that large number of instances manually becomes impossible. This is where orchestration becomes essential, serving as an automated supervisor, making sure those containers run efficiently, communicate smoothly, and recover instantly if something breaks. Docker orchestration is the automated management, scaling, and coordination of containerized applications across multiple servers or machines. In practice, many organizations use both technologies together, running containers inside virtual machines to combine the security and isolation of VMs with the efficiency and portability of containers. Because servers often hold shared data or provide critical services, they are usually governed by stricter security and management practices than desktops. This includes limited local access, role-based permissions, audit logging, centralized updates, configuration baselines, service hardening, and remote administration. If a desktop is compromised, one user is affected first. If a domain controller, mail server, file server, or application server is compromised, the impact can extend across an organization. That is why server administrators place heavy emphasis on patching, access control, segmentation, monitoring, backup validation, and incident response planning. Server management also tends to be centralized. Tools such as remote administration consoles, policy engines, scripting frameworks, and infrastructure management platforms allow one team to manage many systems consistently. Microsoft's server management guidance emphasizes remote and automated administration, including tools such as Windows Admin Center, PowerShell, and other enterprise management services. Desktops can also be centrally managed, especially in large organizations, but they still remain end-user devices first and infrastructure nodes second. Desktop computers are designed to sit near a user, often under or on a desk. Their cases are intended for easy peripheral access and acceptable noise levels in human workspaces. Servers, on the other hand, are commonly built as tower units for small offices, or as rack mount systems for server rooms, MDFs, and data centers. Rack servers are optimized for density, airflow, cabling, and efficient replacement. In many cases, they are intentionally loud because acoustic comfort is less important than cooling efficiency. Blade and modular designs go even further than other form factors by sharing power, cooling, and networking infrastructure across many server nodes. Finally, we have the Hyper-Converged Infrastructure, HCI. This is a software-defined IT framework that virtualizes all components of traditional hardware-based systems. It typically includes virtualized computing through a hypervisor, software-defined storage, and software-defined networking. HCI is commonly deployed on commercial off-the-shelf COTS servers. The key difference between converged infrastructure and hyper-converged infrastructure is that in HCI, both the storage area network and underlying storage abstractions are implemented in software, usually at or through the hypervisor, rather than in dedicated hardware. Because these functions are software-defined and integrated with the hypervisor, resource management can be federated or shared across all nodes within the hyper-converged environment, enabling centralized and unified control. The difference between servers and desktops becomes easiest to see when comparing how each is used in practice. Desktops are mainly used for personal productivity, graphic design, software development, classroom use, engineering tools, customer service workstations, and gaming or media creation. In comparison, servers are used for hosting websites, providing authentication, storing shared files, managing printers, running business applications, processing transactions, backing up endpoints, hosting virtual machines, and supporting collaboration platforms. There is overlap, of course. A very powerful desktop can run a lab environment with several virtual machines. A small business might use a modest tower server that resembles a workstation. Some high-end workstations blur the line by including server-grade processors like the Intel Xeon or ECC memory. Still, the core question remains: is the machine mainly serving a person sitting in front of it, or is it mainly serving users and systems across a network? When choosing between servers and desktops, there are always trade-offs. Servers usually cost more than desktops with comparable specifications because they are built with enterprise-focused capabilities, such as enhanced reliability, manageability, and fault tolerance that are costly to develop, certify, and support. Servers have longer support life cycles. They come with ECC memory support, remote management capabilities, and denser I/O. They champion sustained thermal design, redundant components, and enterprise firmware ecosystems. They also tend to consume more power and require more planning for cooling, rack space, backup strategy, network integration, and security controls. In return, organizations gain reliability, scalability, centralized administration, and better support for critical workloads. Considering to buy a server when a desktop would meet the requirements can be wasteful. Desktops come at a lower upfront cost. They have consumer-grade firmware and shorter life cycles. They have lower power consumption and reduced cooling requirements, simplifying thermal management and infrastructure needs. In comparison to servers, they have limited remote management. If the intended application workload on the computer is small, non-critical, and used by a single user, a desktop or workstation may be more practical because it has a lower overhead. Good infrastructure design is not about always choosing the most powerful hardware. It is about matching the platform to the workload, the risk tolerance, the expected uptime, and the administrative capacity of the organization. So, how to decide if you need a server or not? A desktop is often sufficient when a task is local, single user, and non-critical. A server becomes appropriate when the workload needs to be shared, centrally managed, available for long periods, protected with stronger redundancy, or scaled over time. Questions that help make the decision include: how many users depend on the system? What happens if it goes down? Does it need remote administration? Will it host virtual machines or business databases? Does it require enterprise identity integration, backup policies, or audit trails? If the answer to several of these questions is yes, a server platform is usually the better fit. Here are a few common misconceptions about servers, what people get wrong, and what is actually true. Myth number 1. A server is just a stronger desktop. Not exactly. Performance matters, but the bigger distinction is reliability, service orientation, and multi-user support. Myth number 2. Any computer can be a server, so dedicated server hardware does not matter. Yes, any computer can provide a service, but dedicated server hardware matters when uptime, supportability, and data integrity are important. Myth number 3. RAID means the data is fully backed up. Not necessarily. RAID provides protection against drive failures, but it doesn't safeguard against all types of data loss. Myth number 5. Servers always have no screen or interface. True, many servers can run graphical interfaces, but they are usually managed remotely and configured for infrastructure tasks rather than user-centric interaction. Myth number 6. Cloud means servers are obsolete. False. Cloud platforms are built on servers. They simply package and automate them differently. A server and a desktop are both computers, but they are built for different jobs. A desktop is centered on direct human use, local interaction, convenience, and responsiveness for one person. A server is centered on service delivery, availability, manageability, scalability, and dependable operation for many users or systems. This difference influences everything from CPU and memory choices to storage architecture, operating system design, security controls, and physical form factor. Once that distinction is clear, the rest of modern IT infrastructure makes much more sense because websites, business applications, shared files, cloud services, and identity systems all depend on the same underlying idea. Servers exist to serve.
Thank you for watching this tutorial. I hope it helped. Don't forget to like and subscribe, and I will see you on the next video.